Okay, so to review for this week, we're swapping 3 lectures. So this was going to be next Monday. It's now this, or maybe this was going to be Friday. But anyway, we've moved the d orbitals to, I think, Wednesday, the projection operator to Friday, and then we've moved the practice on the chlorine. It says chlorine MO diagram, but chlorine has been videoed, and so has iodine, I think. And so you can find sort of the halogen MO diagrams videos on Blackboard, also on YouTube. So let's do something that you guys like. Let's do something different if you'd like, or we can do those. But anyway, if you have thought of a molecule that you want me to do, then we can do one that's new, and you guys can kind of see the thought process that goes into making an MO diagram from the atomic orbitals using symmetry as a guide. So those are the 3 things. We start with the atomic orbitals. We use symmetry as a guide to combine them to make the molecular orbitals. So which one do y'all want to do? And if there's multiple ones, we can take a vote. Yes.
Can you do the example from homework 12? It was ethane, or ethene, right?
Ethene. Okay, yeah. It's yes, we'll do it. It's a pretty long one, but we can do that. Let me see if that one is going to be. That would take. I don't even know if we could finish in class if we do that one. But let me pull up the ethene document that's printed out on the wall out here, this poster, and I can walk you through the thinking of it. That way we don't spend all our time drawing. And then we'll do a smaller molecule with maybe fewer atoms. It doesn't sound like ethene's a big molecule, but there are 6 atoms, and so think about all the atomic orbitals we have. Now 4 of those are hydrogens, but we bring in 4 hydrogens, we're going to have 4 symmetry-adapted linear combinations, and then we're going to have the C2. So I'll show you what I'm talking about. So let me pull up ethene. Where would that be? Let's see. Just bear with me while I find the PDF. I'll use the PDF and we can zoom in. Did I put the PDF on Blackboard? Do y'all have that? Like, I'm gonna have to search for it. Here we go. Try to open the PDF and it says Adobe needs to update. So let's see. Let's try it again. Oh, nope, something's happening. Come on. Why is it not letting me? Well, it was mostly in the notes on MO, on the MO versus LB theory. So let's see. I don't know why it's not letting me open a PDF. I have words, but the video is recording, so I don't want to say them. I'll just get the spinning wheel. Okay, well, let's plan B. Let's go back to, well, let's just do it, okay? I won't take the whole time, but I'll go pretty quick. Okay, so the way we do a molecule is we need to first find the character table. So if we have a molecule, we still use the local bond theory and come up with the Lewis dot structure. So our final molecule would be the ethene. And I'm putting it as high as I can get it. I kind of ran out of room, so that's why that H looks funny. But it's just bumped against the limit of my tablet here. Let me draw it. Okay. And so do you know the point group of that molecule? C2H. Yes, C2H. Now, it has a principal symmetry axis that's a C2 and two perpendicular C2s. And so this one particular molecule is a little tricky in that you don't have like a C3 and three C2s. You have a C2 and two C2s. So which one's the principal symmetry axis, right? And it's hard to know. If you look at the character table, the principal symmetry axis is coming out of the board. Oh, that's Z, sorry. Switch that. Okay, and then this is X, and up is Y. Okay. And that's nice because we have that pi bond formed by the two pz orbitals on carbon. Just like in benzene, the z-axis comes out of the plane of the molecule, and it's the pz orbitals that mix to form the pi electron cloud. Okay, so over here, what do we put on either side? Since a diatomic, we have one oxygen atom on the other side, one oxygen atom, and an O2 in the middle. So what do we put on either sides when you have a molecule? You put the equivalent atoms. So in this molecule, what atoms are equivalent? Well, obviously the carbons are equivalent. So you put those on one side, C, and I kind of draw the C double bond to C. And then over here, I have the H, the H, the H, and the H. Those are equivalent. And so let's quickly draw, if we've got four 1s orbitals, the hydrogens are easy. If we've got four 1s orbitals, how many combinations are we going to make of those? It's an easy answer. So if you bring in four atomic orbitals, you get four combinations, okay? So down here at the bottom, all four, what's the simplest way you can put all four of these 1s orbitals together? All of them shaded, right? Okay. I'm not going to draw the H's in there because it's just going to get busy. So I'm just going to draw four unshaded circles. And that's going to be A1G if we go to the character table. Then what's another way I can, so that's going to be one energy for those. What's another energy I can draw with those four orbitals that has one node? Two shaded, half and half. So we'll go left and right. How about that? So this is a way to bring these four atomic orbitals in, and we'll shade half of them, and we'll have one node in the middle. And that's the same size box. The bigger box makes the energy drop, but this has one node, so it's higher in energy. Okay. And then we'll have another combination that has one node. So let's do top and bottom. So this node goes right here. And I don't really know which one of these would be higher in energy or lower in energy, but they both have one node. They would be different though, because, this one, this node here, these hydrogens, are like pretty far apart, right? Whereas over here, these hydrogens are pretty close together. So the node is tighter on this one. So I think it's probably going to be higher in energy, but that's just my thinking. Okay, and then this top one, how do we draw this with two nodes? We got four circles, for the 4 1s orbitals. Diagonal, exactly, yeah. So now we have 2 nodes. And this one's going to be G, right? You see the shaded and the unshaded are going to be in that pattern. So that's going to be, so we need to go get, let's just go get the C2H character table. It's pretty big. Thanks for your patience as I make this new thing. Okay. So quickly, if we wanted to come up now, how we make these orbitals is actually in the projection operator lecture that you see. So what we would do with the projection operator is we would start with a row on the character table, which is right here, and we would pick like a 1s orbital, and we would go through this character table, and we would operate on it. Okay. Okay, we would operate on it. We'd do a C2 and see where that ball goes, right? If we do a C2 around the z-axis, it goes, to the corner, the opposite corner. And if it's a +1, it stays the same shading and so on. And if we do a C2 around the y, we get a -1, so we change the shading. And so we go through all of these different ones. And that tells you what the symmetry of that particular picture is. And so you come in, you run the 4 hydrogens through this table, and you get only 4 symmetries out. And so we would know in generating those 4 pictures exactly what symmetries they are. Now, that's how you actually do it with the projection operator, and that would take a while, and you need that lecture. But we can just look at the pictures and see what symmetries they are if we inspect them. So here's the x-axis right here. You see right here, the x-axis goes left and right. So which one of these pictures changes when going left to right? The second one from the bottom, right? Okay, so it's this one right here. So this one has X symmetry. So we can put that in parentheses if you want. And then we go to the character table and we find X, and that's B3U. Okay, so this one is B3U. This one is varying up and down, so that's Y symmetry. Do y'all see that? Yeah. Okay, and so then you go and find Y, that's B2U right here. B2U. Yeah, and this top one is XY, and so we find XY, and it's right here. So that's B1G. And you can hopefully see why the U's are U's and the G's are G's, right? If I take this circle right down here and move it through the center of mass, it changes shading, and so that's a U. That's Ungerada. Okay, now what do we do for the C2 side? Well, that looks just like a diatomic. And we're going to get those exact same orbitals here. We're going to have the sigma star. So that would be, the 2s together, the 2s out of phase. Okay. And then, again, this is carbon. So that's probably going to have that sp mixing. And so the p orbitals are going to be down here. We're going to have like a px, or no, we'll do in this particular case, this would be like a py in phase with a py. And I'll draw the pz in phase with a pz. So PZ, we draw one kind of in front and then a half moon behind it, and one in front and a half moon behind it to kind of show the Z. So that's PZ. And then the sigma version of the p orbitals is, in this case, because of this molecule, it's got a different coordinate system. So these are the px orbitals. And so here's your two atoms right here. And it's going to be the p orbital on this one in phase in the middle. So the shaded portions are on the outside. And that would be the px. So if it was just a diatomic, the axis of the diatomic would be the z-axis because it's a d infinity h, right? Or a c infinity v. But in this case, we're combining the atomic orbitals on the two carbons in a C2H. It should be D2H, shouldn't it? I'm sorry, I got that wrong at the very beginning. It should be D2H. In a D2H character table. And so those px orbitals that make the sigma bonds, those are px's, not pz's, because this is a different coordinate system because it's a different point group. But it's the same pictures that you would get for a diatomic. And then we have the p antibonding orbitals. So the combinations of the two carbons for antibonding. We have the py's that are out of phase. And the PZs that are out of phase. And then we have that highest energy sigma interaction of the PXs, where we've got p orbitals with an extra node in the middle because they're out of phase with each other. Okay. Now, what are the symmetries of all of these? Well, we could go through and see. This one is the same shade all the way around in all different directions. That's going to be top row or A1G. Okay. This one here, notice it changes along the x-axis. Okay, so it's going to have X symmetry. And we figured that out over here. X symmetry is B3U. The PY, okay, it's going along the y-axis, so that's going to have Y symmetry. That's B2U. The PZ has Z symmetry. We got to go to our character table to find that one because we haven't used it yet. B1U. So it's this one here for the PZ orbitals. B1U. And then this PX, they're coming together, but they're in phase. It looks like an X squared. Do y'all see that? It's a Garada because the way the pattern is, we go find X squared for that one. That's probably the one that would trick you up. It's an AG. I've been saying A1G. These are just AG in this character table, so I'll go change that. This is AG. Now, again, that's the one that I think the others that we've done have been easy, like X, right? And Y, very easy. But is this one easy for you, this AG? The center of mass of the molecule is the origin of the x-axis. So if I look to the right, I see a certain pattern, and I look to the left, and I see exactly the same pattern. And so if we were to square the x-axis, I would look right and see positive numbers, and I would look left and see positive numbers. If we don't square the x-axis, I look right and I see positive x's, and I look left and I see negative x's. I see like a different shading. Whereas here I see the same shading pattern. And so that's an x squared. If you see the same pattern on both sides of an axis, it's squared. That's the thinking. It's my way of helping you cut the corner. It's a shortcut to coming up with why this is x squared symmetry. So I'm going to put that in parentheses too. So this is x squared. And so I go find the x squared piece in the character table, that row, and that row is AG.
So
yes.
If it was like shaded, non-shaded, shaded, non-shaded, would that just be X?
Yeah, let's look up here. This case. So we're looking to the right, and we see non-shaded, shaded. Okay, and we look to the left, and it's exactly the opposite pattern. It looks like it's going in the same direction, but we got to think about how we're looking. We look to the positive X, and we see non-shaded, shaded, and we look left. Now the shaded is close to me. So it's sort of multiplied by -1. So I see the opposite pattern when I look left than when I look right. And so that is X symmetry. And so this one would be X symmetry, and then we go find that as B3U. Those two, I think, would be the ones that I would expect you guys to miss, like if you weren't like really good at it. Okay. And then this one obviously is a G symmetry, and you see this plus minus pattern going around the XY plane. And so that's going to be X times Y. So we go find X times Y, and that's B1G. Yeah, so this one is X times Y, B1G. And then this one is X times Z, because it's in the XZ plane. So we've got to go find that one. That one's nowhere in our that we have. Yeah, X times Z, B2G. B2G. So we've labeled, these are what we call symmetry adapted. There's no room to write this out, but it's SALC, symmetry adapted linear combinations of our atomic orbitals. And then we're going to mix them together. Okay. Now, how do we know how many we're going to end up with the molecule? Well, we've already started with, we started with 4 atomic orbitals on each atom. So we had 8 atomic orbitals, and we got 8 molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Okay, on the C2s. And we started out with 4 1s orbitals over here, and we end up with 4 molecular orbitals. But they're just parts of the molecule. These are the hydrogen parts, and these are the carbon parts. Now we combine them in the middle. So we have 8 over here and 4 over there, so that's 12. So we'll have 12 orbitals in the middle and 12 pictures. So it gets really busy. That's why I made a whole poster out of it in the hallway. But we can do this. The guide for mixing is these symmetries. See the A1G here? That's going to mix with this one. And it's going to mix positive and negative. It's going to be just like our molecular orbital diagrams. And so we're going to have down here, the lowest energy one will just be the ethene molecule. I'm not drawing the carbon labels just because it's still busy. And this is no nodes, right? So all of the 1s's and all the 2s's are all in the same phase with each other, and that electron cloud is just breathing the whole thing. There's no nodes, it's breathing. Okay. Now, how might we combine that in an anti-bonding way? This is also A1 or AG, not A1G, just AG. Let's see if I can get that precision with my eraser. Yeah, got it. Getting rid of the ones. Okay. Are there any other AGs? Yeah, there's an AG up here. Okay. So we'll have 3 AGs. Okay. So then we'll have one here. Now, how would I draw this molecule with these out of phase? Yeah, so it might be like the inner piece is shaded while the outer piece is not shaded. So it's kind of like a radial node. See that these middle pieces on the carbon, the 2s orbitals could be shaded or shrinking while the hydrogens are expanding, and then the hydrogens are shrinking while the C2s are expanding. So that would be an acceptable picture. And then up here, what are we going to do with this one? Well, we've got this AG here. It looks like we could draw the middle piece, and we could shade the hydrogens, and so we could have this business here. And we're going to shade all of that. Do you see how that's the kind of this combination of this one right there, with the hydrogens. So the trick is, if you've got 3 atomic orbitals coming in on either side, you're going to have 3 molecular orbitals. And this keeps you from drawing too many pictures, or not enough. Now this is the most, again, this is like way beyond what I would ask you to do on a 50-minute test. But the skills that we're learning are the same no matter what molecule. We probably have room on this board for 2 more pictures. So is there any combination symmetry that you want me to draw? And then we'll do another molecule. Okay, let's do the XY. So XY is B1G. And over here on the right, we only have one B1G that we can combine it with. So that's great. We're going to have 2 of these, combining. So let's make one that's, super antibonding, and then one that's kind of relaxed in energy. Okay. So how can we combine these guys in terms of their symmetry? So let's draw the low energy one first. So we've got our molecule here. I'm having to draw it kind of big because, so this B1G, we'll just draw it like it is on the carbon atoms. So this one's shaded down below. And this one's shaded on top. And this is dropped in energy from both of them, and so there shouldn't be a node between the p orbitals and the 1s orbitals. They should match the shading. And so I'm going to draw this circle on this one, and I'm going to leave it white. I'm going to draw this one on here, and I'm going to shade it. You see how they interact well because they're in phase with each other. And both of those, even the molecular picture now has the same symmetry, B1G. That's how you would combine them. Now up here, I would draw the same picture, but I would just shade the hydrogen orbital so that there was a node breaking the bond. Am I going too fast? Are y'all keeping up? Okay. So here we would draw the p orbitals on the carbons with the same pattern. And now I'm going to shade this hydrogen right here so that there's a node. So that's high in energy because there's more curvature to the wave function. It crosses 0 more frequently. And so then it's going to be higher energy. So that would be the worst one of those 2 possible combinations. Is it starting to click with you now? It's just the combination of atomic orbitals to make the molecular orbitals. And that's where the nodes come from in the molecule and so on. Now, ethene is a small enough molecule that it does have a pure double bond on it. All of this other stuff is in the sigma framework. All of these orbitals, except for the PZs, are in the plane of the paper that we've been drawing. So we would call those all sigma interactions because they're in the sort of sigma backbone, the CHs bonding or the carbon-carbons bonding and so on. But there is a pure double bond in this molecule because it's small enough and simple enough. And it's this one right here, PZ. This is the double bond. Notice there's no B1U over here on the hydrogens that it can interact with. It truly is above and below the plane. It's not interacting with those hydrogens at all. So this is when it will come straight across in this diagram and be right here, and that will be the double bond, the B1U, PZ double bond. Yes.
If the symmetry of the pi bond is B1, what would be the symmetry of the pi bond orbital?
Yeah, it's right here. So this is out of phase. See, their colors are swapped. and it's XZ symmetry, so that would be the B2G. So you would find XZ. Yeah. So let's practice drawing those, because I've done a correlation of students who can draw a pi bond and students who can't. And students who can draw pi bonds, on average, pass this course. And students who can't draw a pi bond, on average, do not pass this course. There's some mixing. It's not a pure, like one question. I could ask you one question, you pass. It's more complicated than that, but that's an indicator that there's something not clicking with the atomic orbitals. Okay, so let's go to the next page. I'm just going to say, if we're going to draw the pi bond in this molecule that looks like this, just starting out, it's difficult to draw a pi bond that comes in and out of the paper. Okay, so pi bond. So we would draw this p orbital up here and have a shading behind it. You see, it's kind of like a 3D picture. I'm drawing the orbital up front like this. But that's a little hard to see. So let's rotate this molecule. Okay, and I'm going to draw it like this. I'll go ahead and draw this carbons. And I'm going to draw the wedges and dashes. I'm going to draw a dashed hydrogen to the back and a wedged hydrogen to the front. Now, the p orbitals are in the plane of the paper. Does everybody catch that? I've rotated the molecule 90 degrees away from us, and now the p orbitals are easy to draw because they're in the plane of the paper. So up here, the z-axis was pointing out at us, and this was x and this was y. Now the z-axis is pointing straight up. And the x, we rotated around the x-axis, and so the y is going down into the board of the paper, or behind the board. Okay. So can you see how I've rotated the coordinate system? Again, it was the right-hand rule, so this was x, y, z. So z was coming out to you like this. This is the z-axis, and I rotated it 90 degrees. So now the z-axis is up, and the y-axis is going into the plane of behind the board. Okay. So now it should be easy to draw those pz orbitals. So this is the pi bond right here. Now you guys have seen this. We do this in freshman chemistry. Most of us do, and you've definitely used it in organic. And so I don't understand the difficulty in drawing this pi bond. It's a side-on interaction between the orbitals to form a pi bonding association. And then pi star, we can draw the same thing. So they're just out of phase with each other. And they've got this node in the middle. It's let yourself get it, is what I'm trying to say. So this one has Z symmetry, which we determined was B1U. And this one is XZ symmetry, which we determined was B2G. Now, why do I say it's XZ? Well, look at this. Look at this. This is the x-axis here. This is the z-axis here. And I have this pattern alternating plus, minus, plus, minus. And that's the pattern of all of the numbers on the x-axis times all of the numbers on the z-axis. You would have those four quadrants. You'd have positive numbers with positive x times positive z. And you have negative numbers in that section where it's negative x times positive z. Then down below that, you have negative x times negative z, so it's positive again. And then going forward, it's in the other quadrant, it's minus z times positive x, so you get negative. So that pattern plus minus we see all the time, and it's one of these combinations of axes. And so that's how you find it. You find what plane you're in. So if you're in the XZ plane, then that's it right there. Okay, so we could do one of the questions I will put on the test or ask you on the homework is do we have is the pi to pi star transition allowed? Let's see if it's allowed by yeah, it should be allowed by the GU rules. Okay, so let me see, what can I delete? Let's set up the symmetry for X, Y, and Z first. Okay, so well, just in general, we'll have the pi orbital is B1U, and the pi star is B2G. Okay, so we have those two symmetries, and then we want to know X, Y, or Z light can go in the middle. And so we would try this with B3U, B2U, and B1U. So all three of these would go in the middle, and we would do all three of those problems. Okay. So let's have fun with that. Okay. So help me out with the numbers because my memory's bad. Was it B3G?
B1U.
B1U, okay. And let's do X light first. What is the X light on the character table? I guess y'all don't have it in front of you. X is B3U. And then the other one was B2G. Okay. So we're going to simplify these starting from the right. So B3 times B2. We got to find the direct product table. So let me shrink this and go find it. D2H. Here it is. Yeah, there it goes. And let's screw it up. Okay, so now we know what a B3 times a B2 is. So we come over here and we have B3 times B2 is B1. So B1. And U times G is U. Okay, very good. And then we bring this B1U down. And now this is turning out great. So B1 times B1 is A, and U times U is G. We got lucky by picking X. And so the intensity of this transition is proportional to this integral squared, okay? And that's not equal to 0. So not equal to 0, therefore allowed. Yay. And then we could show that Y and Z are not allowed, but I don't want to run out of time. Are there any other questions about the MO diagrams? Again, we did a pretty complicated one. We didn't finish it, but we got it far enough to know that it's just more of the same, okay? But did y'all know where this came from? I mean, this is essentially the MO diagram for a diatomic, okay? And so you should be, if you don't know this piece, then you can go look at the video that shows the MO diagram for a diatomic, and you'll get all of this piece right here. Symmetry guides our combinations. So the A1, AGs and AGs mix, the B3Us and the B3Us mix, and all of that. Every molecular orbital is a combination of atomic orbitals. So it's the 1s's and the 2s's and the 2p's and so on. Or if you're on the third row, it's the 3p's and the 3s's. It's always just the valence shell. So if we're in chlorine or iodine, let's do iodine real quick. Iodine, it's the 5s and the 5p's, not the 1s, not the 2s, not the 3s, not the 4s. So we just ignore all of the core orbitals. They've been sucked in close to the nucleus, so they don't bond. So only the outer shell that's bonding. So that's fine. So really, iodine looks just like this with the swap of those two. And all you got to do is change all of the 2s's to 5s's and all of the 2p's to 5p's, and it's the same picture. Yeah. We're not going to get into the d orbitals. I have a lecture on it just to kind of show you what they do, but that's we just sort of leave that for inorganic. Yeah. Yeah. So we're good. We don't have to do the d orbitals. I have a picture of it just to show you kind of what they do. But yeah, we'll let advanced inorganic, Dr. Zoll or whoever you get. Yeah. I think he's the only one that teaches it. But you've got to remember this stuff when you get to his course, because he looks at you like, why did you learn MO theory? And he comes to me and I was like, I taught them. You can see I taught them. Here's the video. So don't dump that knowledge when you leave the course. Okay, we got a few more minutes. What other questions do you have? Yes, and the 5p's. It would look just like this. Like I was saying, you change all the labels. I didn't actually label these. This should be the 2s and the 2s. Oh, I know what we can do. Okay, so this wave function here is equal to you could say like the 2s on carbon A plus the 2s on carbon B, right? And this wave function is equal to the 2s on carbon A minus the 2s on carbon B. Okay, so that's the little shorthand that we have to kind of describe how we're combining the orbitals. So you can write that in a text editor, like in a Word document, and not have to draw your pictures, but they have the same information. And when they're, and this the convention that I use is when they're in, like when they're mixing well, like when they're in phase with each other, I use the plus sign. And when they're not, I use the minus sign. For like this one would be the 2py on carbon A plus the 2py on carbon B. And then this antibonding one up here would be the 2py on carbon A minus the 2py on carbon B. Is that cool? Is that clear? Yeah, so that you could write that out with subscripts and again put that in a Word document or an article or a paper, and you could communicate how we're combining the atomic orbitals. Now if we get let's do this whole molecule one, like right here. Since there's a node, we'll say it's this whole thing combined with this one, and I'm going to write it out. So this wave function is equal to the 2px on. Oh, this is the one that's kind of ambiguous. I say with they're mixing, so I'm going to use the plus sign. So 2px on carbon A plus the 2px on carbon B. Even though they're swapped signs, you could argue with me on that, and I might lose. Okay, but then this is going to be out of phase with all of the 1s orbitals. So minus 1s on hydrogen A, minus 1s on hydrogen B, minus 1s on hydrogen C, just a second, minus 1s on hydrogen D. Okay, so I've put minus signs in front of every one of the hydrogens to show that they're the same shading. Yeah. Okay. Yeah. and so then I'm saying that there's a node, and maybe, yeah. I just want to use that indicator of minus sign to show that they're all opposite of this one, but yeah. Again, we could argue on those, but this idea of we've got all 4 hydrogens all the same sign, and then the 2 P's are bonding, if you will, and they're the same sign. So yeah. Okay. That's taking us up pretty much to the end. So again, watch those videos. Don't take off the rest of the week because you're going to forget this stuff. Practice. Because I really want y'all to do well on the MO material. Because for some reason it's just, maybe it's artistic. I don't know. People have a hard time with this, and I don't want you to have a hard time with it. Okay. We'll do a review again the Monday after I get back. So a week from now.